In this video, we're going to look at the purpose of volumetric analysis, and we're going to focus on acid-base titrations. So you'll need to know some common terminology. The first one is equivalence point, which is when we have stoichiometrically equal number of moles of acid and base. The second terminology you should know is endpoint, which is when the indicator changes colour. For a titration to be accurate, we need endpoint to match equivalence point. The purpose of the procedure is to determine the amount of an unknown substance. Now this could be a concentration or it could be a mass. And you do this from a known solution. And when I say a known solution, that means you know the concentration accurately and the volume. The procedure itself is called a titration, and it is very accurate. There are some specific apparatus that you need for a titration. These include a pipette, a burette, a volumetric flask, and a conical flask. Now, a volumetric flask come in a range of different sizes. This one represents a 500 ml one, but you can get them in 150 ml, which we used last year, 100 ml, which we also used last year, 250 ml, 500 ml, 1 litre. You get the idea, there's varying volumes. Now the flask accurately knows a volume. And this particular flask, for example, might only have a very small error of plus or minus 0.5 of a mil. So it's an accurate way of making a solution up to a known volume. A pipette is designed to accurately deliver a specific volume. We'll be using fixed volume pipettes, which are like those shown. And the one that we'll mostly use is the 20 ml one, which has a very small error of plus or minus 0.06 mil. You can also have variable volume pipettes, which you can adjust to deliver different set volumes, but we won't be using them in our laboratory. A burette allows you to deliver a variable volume accurately. We'll be using a 50 ml burette, which has an error of plus or minus 0.1 of a mil. The burette itself comes with a tap, which allows you to adjust the amount of solution you are delivering. There are two different types of standard solution. The first one is called a primary standard. Now, primary standard is obviously your first standard. And this is an accurately made solution. There are other types of standards. You can just have a standard solution, which may be a secondary standard or a tertiary standard, and these are solutions standardized from another solution. Now your primary standard is your first standard, and as a consequence it needs to be correct. If you make a mistake here, the error will carry through on every other titration. And as the goal is to be very accurate, you don't want to have an error. So in order to make an accurate primary standard, the first thing is it needs to be very pure and have a known formula. It needs to have a relatively high formula mass. This is to minimize weighing errors. Now, it also can't alter during weighing by picking up or losing moisture. This means you can't have something that's hygroscopic. Hygroscopic means it absorbs moisture from the air, or it can't be deliquescent. And that means it absorbs so much water it turns into a liquid. So that's no good either. The other thing is it can't react with air. Some substances react with things like carbon dioxide in the air. For example, sodium hydroxide would be hopeless as a primary standard because not only does it absorb moisture, it also reacts with carbon dioxide in the air. Now, for acid-base titration, the common primary standards are sodium carbonate, oxalic acid, and sodium tetraborate decahydrate. In our titrations, we're going to be using sodium carbonate. Now, a standardized solution is one that has been standardized from a non-standard. So, for example, if you've made a sodium carbonate solution, you can then standardize a hydrochloric acid solution. Once you have a hydrochloric acid solution that's been standardized, you can then standardize a sodium hydroxide solution, and so on and so forth. Now, indicators are very important in acid-base titrations because the acids and bases tend to be colourless solutions. So if we want to know when neutralization has occurred, we need to use an indicator. Now, the whole point of an indicator is so that endpoint, which is when the indicator changes colour, matches equivalence point. An equivalence point is when we have stoichiometrically equal number of moles of acid and base. And what I mean by stoichiometrically is it's in the ratio of the equation. A common indicator that we use in acid-base titrations is for methyl orange. And this is when the equivalence point is in the acidic range. Now, you get an equivalence point in the acidic range when you use a strong acid with a weak base, because this will give an acidic salt. Now, it changes about pH of 3.3 to 4.4, and on the acidic side it's pretty red, and on the basic side it's a nice looking yellow. Another really common indicator that we use is phenolphthalein. Phenolphthaleine's equivalence point is in the basic range, so we tend to use it when we have a weak acid and a strong base, because this will give us a basic salt. So it changes about pH of 8.3 to 10, and on the acid side it's colourless, and on the basic side it's pink. What we're going to do now is we're going to look at a procedure for standardizing sodium hydroxide. So in this procedure, we'll make a primary standard of sodium carbonate. We'll then standardize hydrochloric acid from the sodium carbonate, and then we'll standardize sodium hydroxide from the hydrochloric acid. So in the first step, we're going to make a primary standard. So in this procedure, we're going to dissolve 1.336 grams of sodium carbonate in distilled water and make it up to a volume of 250 ml. So from here we can work out the number of moles of sodium carbonate is equal to mass over formula mass, and it's 1.336 over 105.99, and this will come out to 0.012605 moles. From there we can find the concentration of our solution, is equal to number of moles over volume, which is 0.012605, divided by the volume of 0.25, 250 ml, which comes out to 0.05042 molar. The next step is to standardise hydrochloric acid. So we know our hydrochloric acid is approximately 0.1 molar, but we don't know exactly. So what we're going to do is we're going to take 20 ml sample of sodium carbonate. Now, because it's an exact volume, that exact volume goes into the conical flask. So we know this has got 20 ml of sodium carbonate, and we know from our previous calculation that the concentration is 0.05042 molar. We know that accurately because it's the primary standard. We are now going to titrate our hydrochloric acid, and we know that we had 19.02 ml. So, first step in any stoichiometry is we need an equation. So we have two hydrogen ions react with carbonate ions to give water plus carbon dioxide. Now this will be an acidic equivalence point because the carbon dioxide can dissolve in water to give carbonic acid, and that will make it acidic at equivalence point. So because it's acidic at equivalence point, we would have to use methyl orange indicator. So let's do the calculation. What do we know? Well, we have enough information to find the number of moles of sodium carbonate. So the number of moles of sodium carbonate will equal the number of moles of carbonate, which equals CV. So this comes out to 0.05042 times 0.02, which comes out to be 1.008 by 10 to the negative 3 moles. Now, using the equation, we can see that 1 mole of carbonate reacts with 2 moles of hydrogen ions. So, the number of moles of hydrogen ions will be twice as many. From there we can find the concentration of the hydrogen ions, and because it's monoprotic, this will also give us the concentration of the hydrochloric acid, which is equal to N on V, which is equal to 1.008 by 10 to the negative 3 divided by 0.01902 of a litre, which comes out to 0.1060 molar. Now that we've standardised our hydrochloric acid, we can now standardise our sodium hydroxide, which is about 0.1 molar. So we are use 21.14 ml of the hydrochloric acid. Now this isn't an exact volume, so that was in the burette. So our burette contained 21.14 ml because it's a variable volume. Its concentration, which we worked out previously, was 0.1060 molar, and this reacted with 20 ml of sodium hydroxide. Now we know the sodium hydroxide is in the conical because it's an exact volume. So we need an equation. Hydrogen ions plus hydroxide ions gives water. We can do this because we have a strong acid with a strong base. So the number of moles of hydrochloric is equal to the number of moles of hydrogen ions, and this is our known because we've got a concentration in our volume, which is equal to 0.1060 times 0.02114, and this comes out to be 2.2408 by 10 to the negative 3 moles. Now this is a 1-to-1 ratio, so the number of moles of hydroxides is the same. And therefore the number of moles of sodium hydroxide is the same. So our last step is to find the concentration of the sodium hydroxide solution, which is equal to N on V, which is equal to 2.2408 by 10 to the negative 3 divided by 0.02, which comes out to 0.1120 moles per litre. And we had four significant figures previously, so we have 1, 2, 3, 4 significant figures. It's time for you to try some yourself. We're going to be doing some titrations in the lab over the next few days. Try some calculations from the OneNote, acids and bases, volumetric analysis, acid-base titration calcs. The worked answers can be found on Space by clicking the link, and if you're ready, it's time for Star Set 15. Good luck.